Okay, guys, this is going to be the notes on polymers and plastics. So if you've already done part of those notes, then you can skip to the other part and just do that part. But we'll start off with polymers. So we're going to take notes on both topics, and then you can submit those in Canvas. Okay, so first of all, polymers is a part of organic chemistry. That's why we're doing this, okay? And so we're going to talk about this specific part. They are carbon-based molecules, and carbon can form many molecules. If you remember before, we talked about this when we introduced organic chemistry. There are over 10 million known compounds made out of carbon, okay? Including very large chains of many varieties called polymers. Very large chains of many varieties called polymers. So polymers are these very large chain molecules that are carbon-based, okay? So now we're gonna go ahead and define that word, polymers. This is a two-part word. Two-part word. You've probably seen that prefix before, poly. And hopefully that sounds a little bit familiar to you, but poly means many. Okay, so the prefix poly equals many. And the suffix, the ending there is just mer. And that is, has a Latin root for unit. Okay, so polymer is many units, okay? So many units. So to define, to give you a straightforward definition instead of just breaking the word apart, okay? They are large macromolecules, okay? You have seen micro many times. Microscopic means so small you can't see it. You need a microscope to see it, right? Macro is large. It's the opposite of micro. So large macromolecules. Some of these you can actually see with the naked eye. You don't actually need any microscope to see them. The molecules are so huge. Large macromolecules made of repeating units called monomers. And the prefix mono means one. So the units that you put together in a chain to make a polymer are called monomers. So each link is a monomer, and then you put them together, you make a big chain, that would be your polymer. Okay. They can be, spell right, they can be large enough to see with the naked eye. They can be large enough to see with the naked eye. Many can be seen with low-powered microscopes. So they can be large enough to see with the naked eye, and many of them can be seen with low-powered microscopes. Polymers exist in nature. Polymers exist in nature, but many materials that we use, in our daily lives are synthetic polymers. Synthetic polymers. And remember that word synthetic, we've talked about it before. If you don't have a good memory for those kinds of words, just in parentheses, synthetic means man-made. Okay. So synthetic polymers are man-made. So they do exist in nature. There are polymers that we did not make as humans, okay? But there are a lot of polymers that we make to use in our daily lives. And we're going to talk about those. So let's just go into those two categories. We'll start with natural polymers. Examples. Natural polymer examples. DNA. DNA is a natural polymer, so that's something that you've learned about in biology, okay? These are made of repeating nucleic acids. Made of repeating nucleic acids. I'm going to underline that piece right there. So the nucleic acids are the monomers that connected to each other make the polymer DNA. Okay, so DNA is a polymer, the nucleic acids are the monomers. Okay, proteins. Proteins are an example of a polymer, okay? A natural polymer that animals make, plants make, okay? Proteins are made of repeating amino acids. Made of repeating amino acids. So the amino acid then is the monomer, protein is the polymer. Starches. Starches are a common part of a plant. Starches are made of repeating sugar molecules. Repeating sugar molecules. When you take a bunch of sugars and you string them together and chemically bond them together, you end up with a starch, and the starch is a polymer. The sugars are your monomers. Cellulose. Cellulose. This is plant fiber, just if you haven't heard of cellulose before. Okay, plant fiber. This is also made of repeating sugar molecules. Now, plant fiber is something that we cannot digest as humans. We can digest simple starches, but we can't digest cellulose. So when we eat something like celery or well, any plant product that we're eating that has cellulose in it, that cellulose goes right through us. That's the fiber that helps keep us regular. And the last natural polymer example is latex. Now we take latex in a lab and we do things to it to make it more useful to us, but latex is actually the name of natural rubber. You can find it in a rubber tree. It's a liquid. It's not useful at all. If you think about like a latex swimming cap or latex gloves, we have definitely changed the latex to make those items. So latex in its pure form, natural form, is not a swim cap or a glove. It is definitely a liquid. So, but anyway, it's natural rubber. It is a polymer and it is made of repeating isopropene molecules. Okay, made of repeating isoprene. I don't know why I did that. My apologies, okay? Isoprene molecules. Okay. Before I move on to the next bullet, I just want to put a little note here, a little starred note. Okay, the underlined portion in each description represents the monomers that form the described polymer. The underlined portion in each description represents the monomers that form the described polymer. So DNA is the polymer, the nucleic acid is the monomer, proteins is the polymer, amino acids are the monomer. And so I want you to have that reference that this underlined piece is the monomer that makes up each of these polymers that we were listing here, these natural polymers, okay? So, got to get my formatting here. All right, let's talk about synthetic polymers. So synthetic polymer examples. Okay. I'm just going to kind of go in categories here. So cloth polymers. Examples could be nylon or polyester. when you look at polyester, this name actually tells you what the monomer is. Ester is the monomer. Polyester is when you take a bunch of esters and you combine them with each other molecularly. So polyester is the polymer, ester is the monomer. So I just underlined that to keep it consistent. Okay. Synthetic rubber. Synthetic rubbers like tires, oops, shoes, the soles of your shoes are typically made out of a synthetic rubber. Silicone. Okay, a lot of people see, let me just take that E off. A lot of people see this word silicon and they think silicone. Silicon is an element, it's on the periodic table. It is absolutely not a polymer. It is not made out of carbon. It is its own element. Silicone, when you add an E there, this becomes an entirely carbon-based substance. So you might have seen it again in a swim cap type of thing, or a lot of times like hot hands that you have at home to take things out of the oven with can be made out of silicone. So silicone is a rubber, it's made out of carbon. The word silicon means something totally different, and it is Silicon Valley because we use silicon in microchips. And so that's why that valley has that name, that technology hub of our country, okay? Plastics is another category of polymers. So this is, you know, we've been making plastics for the past couple of weeks of class and testing them, and plastics are a type of polymer. So we're going to get into those a little bit before you finish answering questions about your making plastics lab. So PVC is a type of plastic that you might be familiar with. That stands for polyvinyl chloride. Polyvinyl chloride. And again, if you look at just the piece after that poly, you get vinyl chloride. That is your monomer. PVC or polyvinyl chloride is the name of the polymer, okay? Plastic wrap, like saran wrap, for example, that has a chemical name of polyethylene. Computer is very smart here, okay? So polyethylene is the chemical name for plastic wrap. Ethylene then is your monomer, polyethylene being the polymer. Polycarbonates are a type of plastic that's very common. I'm not going to write the what polycarbonate is the chemical name for that, but I'm going to just write their uses. Used in cell phone cases, glasses, lenses. So if you're wearing glasses right now, they're probably a polycarbonate lens instead of like a glass lens. They used to be glass, which is why we call them glasses, but they are now using polycarbonates as their lenses because it's a little bit safer. You can also get a much better focus for whatever your prescription is out of a polycarbonate, much easier to get that. Traffic lights. If you've ever seen a traffic light up close, the big bulb around the lights, that is a polycarbonate. And many, many, many more things. Oftentimes a hard water bottle will be made out of a polycarbonate, things like that, okay? And I'm just gonna add many more, and I'm emphasizing the many because there's so many types of plastic, it's crazy. It's definitely a large portion of those 10 million carbon-based compounds, okay? Okay, so now we're gonna go into plastics. And you can start a new page. If you've filled up a page, you can start a new page, or you can continue on this page, but we're going to, this is its kind of own standalone topic within polymers, plastics. Okay, so first off, a definition of plastic. We haven't really talked about this quite yet, but it is any material made of organic polymers. Any material made out of organic polymers. So remember, organic means carbon-based, which every polymer on this list is carbon-based. That's why they're polymers. That's why they're organic, okay? Polymer means a long chain molecule made out of repeating stuff. Okay, so any material that's an organic polymer, but we have to keep going because DNA is not plastic, right? And neither is nylon. So we have to keep going with this. So any material made out of organic polymers that can be molded into solid objects with a wide range of properties. that can be molded into solid objects with a wide range of properties. Okay, we're going to be able to classify plastics into multiple different categories. So the first way I want to classify them, there are two major categories of plastics. The first one is petroleum-based. Petroleum-based plastics. So you may or may not have learned before that many of our plastics are made from petroleum. Yes, oil that comes from the ground. We turn some of the parts of petroleum into plastic, okay? So petroleum-based plastics are made of petroleum that has been chemically treated, to form cross-links, and bonds to make a solid. That's a really oversimplification of this process, but you chemically treated it. That could mean so many things, and it does mean so many things depending on which plastic you're making, to make cross-links, to make bonds, and to form a solid. So you're taking these big glugly molecules out of this liquid petroleum, and you're treating them in a way that make them bond with each other, and these molecules are all interwoven, forming these bonds, and then you've created a solid, and that's your plastic, okay? Now, depending on what those chemical treatment steps are, you're gonna end up with polyethylene or polycarbonate or, okay, PVC. All the different types of plastic have different routes to create them, okay? Most plastics are petroleum-based. Most plastics are petroleum-based. The vast majority of the plastics that we make right now are petroleum-based. Hopefully, before I'm done teaching, that will change and there will be more of our other category here. But our other category here is bioplastics. So hopefully, if you know petroleum-based plastics are made out of petroleum, you might be able to guess that bioplastics are made out of biological things, plants and animal products, okay? So bioplastics are a new way to make plastics from plant and animal materials. This makes them a renewable resource. Okay? We don't have to rely on finding petroleum, which again has been buried in the ground for millions of years, and using the petroleum to make plastic. We can use plant and animal materials that we already have that we can grow and refresh in just a matter of a year or a couple of years in order to make these products. Okay, more facts about plastics. Plastics decompose very slowly. We're talking about 400 to thousands of years. Because of their very large molecules. Okay. This is kind of similar to if you think about when you eat. If you eat simple things, simple sugar, they get into your system like that. The simpler the substance that you're eating, the faster your body can break it down and process it. If you eat more complex things, proteins are a lot harder for us to break down and process. Fats are easier than proteins, but they're not as easy as sugars. They're harder for us to break down. And when you get into things like fibers are too complicated for our systems to be able to break them down. So similarly in nature, things that are more complex are harder to break down than things that are not. The leaves that fall in the fall, they'll break down into your grass a lot easier than a twig that falls off of the tree in the fall. It's going to take a lot longer for that more complex thing to be broken down, okay? So plastics take a very, very long time to break down. And this makes recycling is very important. If we don't recycle ever, we're going to run out of material, especially when we have things that are petroleum based. There's a finite amount of that. Okay. Common misconceptions. People think bioplastics biodegrade, right? That is not necessarily true. So bioplastics do not decompose faster than petroleum-based plastics. Okay. It is not bioplastic because it biodegrades. It's bioplastic because it's made out of biological things, plants and animals. But when you create a plastic, when you create this polymer that's cross-linked, then you've created something that's going to take a long time to break down, no matter what you created it from. Okay. Biodegradable plastics, because those do exist. Biodegradable plastics can be broken down faster if there are specific bacteria and conditions present. Biodegradable plastics can be broken down faster. So that's not a bioplastic, it's a biodegradable plastic. You can form a plastic that is biodegradable, but all of those plastics have to have very specific conditions. Certain types of bacteria have to be present, certain temperatures, certain moisture levels, certain amounts of sunlight. Those are very, very specific. They might not necessarily break down in a landfill, okay? So you're gonna actually see that. If you have a biodegradable plastic packaging on something, it will tell you on the package, you know, not in a landfill. It'll say in specialized landfills, or it will say under the right conditions. They might literally just say that. So just be aware of that. If you're buying something because you think its packaging is going to biodegrade, make sure you read it carefully. Okay, let's go into properties of plastics. We had these when we were testing, or if you haven't done this yet, but you might be testing soon, the properties of plastics that you've made in the lab. Okay, and I wanted to make sure that you had these properties written in your notes so that you don't have to find them back in a lab somewhere when we're taking our exams. So properties of plastics. So water resistance. And most plastics, oh, did I spell that wrong? Yep, extra I. Okay, water resistance. Most plastics are water resistant. Most plastics are water resistant. Now, it does depend. You can be making a plastic that you want to be absorptive and it will absorb water, but that's less common. Usually when we are using a plastic, when we're making a plastic, we're making one to be water resistant. So most of them are water resistant, but again, not all. And that's going to be kind of the trend in all of these properties, okay? Transparency. So again, this is the ability for light to shine through, right? So ability to transmit light, right? Plastics can be made in any transparency. You might have noticed, or you will notice, that depending on how much coloring you add to your plastic samples, its transparency is going to be affected. If you don't add any coloring, it's going to be much more transparent than if you add coloring. But the type of plastic also matters as well, right? Like polycarbonates. If you are making glasses lenses, you want them to be very transparent. Otherwise, what's the purpose? You know, you're trying to get them to help someone's vision, not impede it. If you're making a plastic for a water bottle, you could want it to be transparent, or you could want it to not be transparent. It kind of just depends on the design that you're going for there. Plastics that are used to create cars, okay? The body of a car is highly plastic now. We probably don't need those to be see-through. We want those to be opaque, okay? So they can be highly transparent or they can be highly opaque. It can be anywhere in the middle as well, okay? Flexibility, you're bending without breaking, right? They can be highly flexible or highly rigid. And again, you might see some of that in making plastics in the lab. You might have samples that were very, very floppy, flexible, and you might have samples that were super rigid and you try to bend them and they break. Okay, so similarly, you can have, I mean, even just in water bottles, most water bottles are made to be on the more rigid side, but you can flex some of your water bottles, especially disposable plastic water bottles. But there's also water bottles that are designed to be flexible. Like if you ever go backpacking, you can get water bottles that you can actually roll up to save space once they are empty. So highly flexible, highly rigid. Again, it depends on the purpose of that plastic that you're making. All right, plasticity. Now this is a property that all plastics will have. Okay, so all plastics have the ability to be permanently deformed without breaking. Because that is the definition, to permanently deform it. We said that molding it, that's another way to say this. If you can mold it into a shape, then it's a plastic, a polymer that can be molded into a solid shape. All plastics have that ability. Now, sometimes you can permanently deform a plastic. Like if you take a plastic bag, you can shove your thumb into that plastic and deform the plastic. You can change its shape. When you pull your thumb out, it's got this little weird bubbly part to it now. And it's not broken, but it's deformed. So sometimes you can do that deformation at a room temperature, small effort place. But if not, that doesn't mean your plastic isn't plastic. You might have to raise the temperature. If you can picture taking a plastic to a flame and you can melt it. If you leave a plastic sometimes in a hot car in the summer, it can be deformed the next day when you get it out. Okay, so all plastics have this ability. It just depends on whether it's at room temperature or at a higher temperature. Strength. Again, what are you making your plastic for? So they can be made with high or low strength. It just depends on the purpose. A good example, why would you ever want to make one that's low strength? Well, if you picture the spider webbing that you kind of hang all over your house and your fence at Halloween time, that you don't want that to be super strong, because then you wouldn't be able to stretch it out and make all these crazy cool effects with this plasticky spider web stuff. So that's just one example of a low strength plastic. But high strength is typically more sought after, but also things like plastic wrap. You want the plastic wrap to have a little bit of flex. If you make it too strong, it's going to be more on the wanting to break side than on the stretch over a bowl side. So strength and flexibility sometimes are counteractive there. And then the last one we were testing was elasticity. Elasticity. Okay, again, picture a rubber band is elastic. You stretch it out. As soon as you let go, it will go back to its original shape. Okay, so some plastics are highly elastic. Can't type today. They will return to their shape after a slight deformation. Okay. So some plastics are highly elastic in certain shapes. It can make them bouncy. So again, one of the examples that I like to use is I will take one of my magnets here. Okay, so we have this just a plastic ball that has a little magnet in one end. Okay, and when I take this, I can't deform this with my fingers, at least not apparently to me. Okay, but if I drop this on my desk, let me give myself a space here. If I drop this, okay, it bounces up. That's because when it hits the desk, it will flatten. It gets a slight deformation from that force, and it will go back to its original shape, which causes it to bounce back. So it gets, we've got this round, trying to show you here, got this round, it gets a little bit flattened on the table, but then it goes right back to round, and that causes it to bounce back up. So in certain shapes though, if I had made this exact same type of plastic, which I would strongly hypothesize this is a polycarbonate, but if I made this in a different shape, a flat shape, it might not bounce at all. So it depends on the shape, it depends on the type of plastic, and again, it just depends on what you're making that plastic for. So all of these properties depend on a lot of things, and they can be very present or very not present in a plastic sample, depending on what you're making it for. This is the one, plasticity, that all plastics have, but that one depends on whether we're talking at room temperature or high temperatures. Okay. So that is the end of our notes for polymers and plastics. Hopefully you got all those written down, refer back as needed, and you can submit those when you're done. Thanks.